Techniques in later videos provide analytic insight into the time evolution of some dynamic systems, but the quantitative description of many systems still requires numerical integration. Use this video to develop intuition about how software packages can calculate the dynamics of a system over time, and use this video to outline a MATLAB program for simulating a toy model of gene transcription and translation. We want to solve for the long-term dynamics of a system starting with knowledge of how the system changes in time and the initial condition from which the system begins to evolve. Consider a one-dimensional cartoon. Here, the state of the system is characterized by a single variable x. We use the differential equation to relate the rate of change of the system to its immediate condition. The time derivative of x around time t can be a function f of the immediate system state x and possibly even of time t. The initial value of the state is x sub 0 at initial time t sub 0, and we want to solve for the state x at other times t. We want the function x of t. Draw the direction field of quivers, meaning arrows, corresponding to the slopes prescribed by the differential equation for dx dt. The greater the value of dx dt evaluated at a particular system state x and time t, the more positively sloped and steeper the arrow originating from that point. How can we calculate the shape of the curve that passes through the state x0 at time t0? Indicate a horizontal length h originating from the initial condition. Highlight a quiver indicating the slope through this point. Euler's method extends the quiver to form the hypotenuse of this right triangle with base of length h. The red circle marks the approximation to the state x at a time step h following initial time t0, obtained using Euler's method. One can easily appreciate that the red circle is a poor approximation to the correct value. The right triangle is about 2 times too tall. We can refine the calculation by moving back halfway between the red circle and the initial condition and drawing a quiver to indicate the slope associated with this intermediate location. Copy and paste the quiver to the initial point. Use the yellow slope to draw a right triangle that provides a more accurate second-order estimate of the state x at time t0 plus h. The slope associated with the orange circle provides a more accurate result in this case because it more accurately represents the average of the changing slopes that the trajectory encounters as it travels from time t0 at the left to time t0 plus h a short distance to the right. The red quiver indicating the slope associated with the initial condition does not as accurately characterize the variety of slopes encountered moving between these times, because the slope is decreasing in this region of the direction field, and so the red slope is biased. It's too steep. It overestimates the slopes that the trajectory displays during this interval of time. Repeating the process estimates a subsequent value of x after an additional time step. Likewise for this iteration. Taken together, a series of iterations roughly outlines the actual trajectory of the state of the system through time. Because we plot the actual gray-blue curve and the approximate yellow curve together, we know that we can trust the second-order approximation method in this case to provide qualitative information about the actual solution, but not necessarily quantitative precision. We know the capabilities and limitations of the yellow approximation because we already know the actual solution. Why would we bother calculating the yellow approximation if we already knew the exact solution? In a more practical situation, we obtain the yellow curve precisely because we do not have access to the exact curve. In such situations, how can we trust the yellow curve to represent the actual solution accurately? We can introduce quality control to the numerical algorithm. Here is the red triangle associated with Euler's method, and here is the yellow triangle generated with the help of the orange circle. the computer can calculate the distance between the red first-order estimate and the yellow second-order estimate. In this case, this discrepancy is a large, actually a majority fraction, of the vertical distance between the red first-order estimate and the initial height x0. Because the first-order estimate is a poor approximation to the second-order estimate, we intuitively suspect that the first-order estimate is also a poor approximation to the actual height of x at time t0 plus h. The second-order method was required to generate a large improvement over the first-order Euler method, leaving us to wonder whether there is still much improvement remaining to be achieved by inventing and executing some sort of third or perhaps even fourth-order method. We do not tolerate the fact that the length of the orange double-headed arrow is a majority fraction of the length of the red double-headed arrow, so we try a shorter step in time, for example h divided by 2. The second-order estimate is now much closer to the first-order estimate. The vertical discrepancy pointed out by the orange arrows is a small minority of the first-order estimate of the change in x owing to a change in time h divided by 2. The improvement over the first-order estimate afforded by the second-order method is a small fraction of the overall change in x, suggesting, at least to loose intuition, that little improvement awaits to be achieved through higher-order approximation methods, and suggesting, thus, that the yellow circle is close to the correct value. Readjusting the step sizes in an ongoing way, shortening them to ensure accuracy when the first-order and second-order approximations disagree, or instead extending the time steps to avoid unnecessary computations when the first and second-order approximations are already closer than we require for a particular level of analysis, we can trace out a curve that judiciously spends computer time to outline the features of the dynamics of the system. Modern numerical integration methods make available multiple orders of refinement and adaptive readjustment of step size to within user-specifiable tolerances to provide accurate curves suitable for production quality research. Hopefully, the numerical computations are efficient. The direction field in this example is reasonably simple and physics-looking. Physicists think that everything is continuous, infinitely differentiable, analytic, and so on. However, one can worry about mathematically pathological direction fields that don't work well with the numerical integration method and thus cause adaptive step sizes to shrink to very short steps. These situations require very large numbers of computations. They are computationally expensive. If you find these ideas interesting, you might want to search the internet for the word stiffness. Having established intuition about what's under the hood, let's now outline the pieces of programming that one encounters when using numerical integrators on a day-to-day basis. In this example, we will outline the organization of MATLAB scripts that you can use to calculate the dynamic levels of messenger RNA and protein in a toy model of gene transcription and translation. We will carefully derive this system in the next slide deck, but for now we take it for granted that we are interested in using a pair of differential equations describing the rates of change of the levels of protein Y and messenger RNA Y sub m to calculate the levels of these molecules at various times t, starting out with knowledge of the levels of protein and messenger RNA at an initial time t equals 0. The differential equations contain terms and parameters describing transcription, messenger RNA degradation, translation, and protein degradation. We organize the MATLAB program into two scripts. In one script, we tell MATLAB the initial conditions and ask for the dynamics of the messenger RNA and protein levels using a command that says, basically, use a numerical integration method and the initial condition I just told you to integrate the system of differential equations specified in a second script. Then plot the results. In this video, we will avoid literally reading the scripts line by line. We will simply walk through their general organization. The script on the right depends on outside input to specify rate coefficient parameters and the current state of the system. Here, y is a MATLAB vector with two elements. Element 1 is the amount of messenger RNA, and element 2 is protein level. This MATLAB function spits out a vector whose first element is the time derivative of the messenger RNA level and whose second element is the time derivative of the amount of protein. The script genede.m specifies the system of differential equations in this example. We have to tell MATLAB to do something with genede.m. For this example, we will call the script on the left run genede.m. Run genede.m specifies parameter values, duration, and initial conditions for a simulation, and tells MATLAB to integrate the differential equations using the other script genede. Run genede.m also instructs MATLAB to make pretty figures using the results. By writing simulation parameters and differential equations in separate files, we avoid accidentally altering the structure of the differential equations when we edit and explore parameter values. In this video, we have developed a rough intuition for how numerical integration works and what it looks like to work with on a day-to-day basis.